So the talk session of today's session is really to talk about the continuous delivery of IoT sensors. And Ulf from Red Hat, Ulf would be taken on to talk about the subject. In few words, Ulf is a software engineer at Red Hat. He's part of the research and products team, where he currently he's focused on Rust and embedded. When typically he's not working on useless hobby projects involving embedded, he's with his 2 kids, 2 dogs, and a wife. He loves music and play guitar when time permits. I think I should have asked Ulf to dedicate a couple of minutes to play some guitar, but probably another time, not today. Ulf, the mic is yours.
Thank you. Today I'm going to talk about continuous the delivery of IoT sensors. And I realized after writing the presentation that actually I meant continuous deployment of IoT sensors. So I'll go through the definitions in a bit. You will see how the different parts of a system built for doing continuous deployment functions and which parts you need in order to build it. And I really believe that we can improve both the security and reliability of IoT systems if we plan a system like this from day one. So as was mentioned, I'm a software engineer at Red Hat, and we do work on the Drogue IoT project. So the Drogue IoT project is a kind of a rethink of how to do IoT in a cloud native environment, and being able to not only handle events from IoT sensors, but also manage the devices, providing extensions to different other open source projects, but also providing this level of integration you get from device to cloud, which we'll see in a bit. So what do I really mean by continuous delivery and continuous deployment? So I think of this as 3 different types of sub-cycles within a software development. First is the continuous integration, where you develop some feature, you have some automated tests for it, and then you merge the code into your repository, and maybe you have some automated system for doing the tests and so on, and you do this continuously. So that's continuous integration, the thing you see in green on the slides here. And then continuous delivery, you add another step where you create this releasable artifact. In the embedded case, typically this is the firmware, right? And then this artifact is ready to be pushed out to the firmware. And then you have the final step, which is the deployment, continuous deployment, where you take this releasable artifact and automatically deploy it in your system. And this is a very, let's say, standard practice in a lot of regular software systems, whereas it might not be that, let's say, widely used in embedded systems, and we'll shortly see why. But it's really powerful because you can easily update the system in this way, and then the fewer humans that are involved in this process, the better. So what do I mean when I say microcontrollers and embedded systems? So typically these devices have very little RAM, in the order of a few kilobytes, and then also very little storage. So this impacts how big the firmware can be, which we will see is also important when you consider the capability to do in-place update. They don't have an operating system and to handle, so there's no Linux running on the under the firmware, and there's also no memory allocator, or you have to provide one yourself. So why would you want to do continuous delivery of these types of hardware? The most obvious thing is there are bugs, even in embedded development. There are also security fixes, and maybe a good example of a thing that's very important to or a thing that can be solved using firmware updates is things like changing the root certificates of the IoT service that you might be using, right? So it's important to be able to keep the devices up to date. So what are the impacting factors for being able to do firmware updates? So why is this let's say not that as widely adopted in embedded systems? And the first factor is risk. Testing a new firmware revision might take a lot of time. It might need some manual intervention. It's physical hardware involved, so tests might be also very unstable. But maybe more importantly, when you're actually updating the firmware, you can risk that the device stopped working and you don't have any way to roll back because there's no operating system and things like that. So you need to be careful, basically. And also, a lot of the firmware written today is written in C, which is also not the most bug-free language you can use in embedded. So that's another factor that you can easily introduce bugs in such a code base. Another factor is resource usage. As I mentioned, the amount of memory and storage you have on these devices is quite low. So you might not have the ability to do firmware updates if you need to spend some of your flash on a bootloader or half of your flash on a second flash bank for the next firmware. So that's also a factor here. Not all of the devices are connected. So if your device is not connected, you might not be able to do firmware upgrades at all. You might be able to handle it by adding some additional module that talks to your device over a wired link. But another part of connectivity is the bandwidth. If you're using something like LoRaWAN, the amount of bandwidth that you have available to your system might be very low. So you you typically would need to spread out the firmware updates over a longer period of time. And finally, the tooling for embedded is also, let's say, spread out. It depends on which vendor you use. How can you easily build and deploy or build your applications like your embedded firmware application like you would build any regular software? And you need the CI/CD tools to support that. And running things on modern platforms like Kubernetes might not be that easy. So how can we handle the risk factor? So basically, we need to reduce the risk. We need to make sure that we have automated testing on the device. We need to make sure that our device can support rolling back to earlier version or rolling forward to newer version, just like regular software. And we can increase the confidence in our code by, for instance, using a programming language like Rust, which I'm very fond of. So in one word, you just want to make it boring, just like any other application. Resource usage, you probably want to make sure you use a programming language that doesn't take all the resources on your embedded device. This has traditionally been C and C++, but with Rust you have a language that also reduces the risk of a lot of big classes of bugs. For connectivity, there's a lot of options. You have the long-range technologies like LoRaWAN or LTE, where you might want to spread out the firmware updates over time. You have Wi-Fi available in many locations, and in that case, it's pretty easy to do firmware updates. If you have this local networks like Bluetooth or Thread, then you need some capability in your gateway, perhaps to handle multiple devices and also a custom protocol for updating the device. And for tooling, there's a lot of open source projects out there. There's Kubernetes for running the software in the cloud. There's Keycloak for handling authentication and authorization of your devices. Kafka you can use for telemetry data. Postgres you can store device information. Firmware, there's Eclipse hawkBit, which allows you to store firmware artifacts and handle updates, and you can use Eclipse Ditto for digital twins. But these are all kind of separate things, and one of the things that Drogue Cloud attempts to solve is to bridge this together in a single IoT platform that you can use to provide both connectivity and firmware updates and other integrations if you wish. So Drogue Cloud, the one part of it is the connectivity and integration, where on the left side here you have the devices, gateways, and third-party services that ingests telemetry data via the Drogue Cloud protocol endpoints. The cloud authenticates the devices. It forwards the events to a streaming system like Kafka. And then on the right-hand side, you have the cloud applications which talk to the Drogue Cloud either via Kafka, MQTT, or WebSockets. And you can process these events in the way you want to. And then on the other way, on the way back, these applications can send commands back to the devices. And these are the foundations from which we build this firmware update capability on. You can also do device management. Basically, you have devices which can be any kind of device. It can be regular devices. It can be gateways. These are grouped into what we call applications. And then you can manage all of that through a REST API or a console. You can also manage the workloads on the edge. So let's say you have a lot of gateways which you want to manage. You can use Drogue Cloud to, in combination with Open Cluster Management, which is a Kubernetes add-on for managing other clusters. And then you can run these tiny editions of Kubernetes like Microshift or K3s on your gateways, and Drogue Cloud can schedule these IoT workloads on the edge. And finally, we have firmware management, which is, as I mentioned, built on top of the connectivity layer, and this means that we get firmware update capability for CoAP, MQTT, HTTP, LoRaWAN devices. Anything that plugs into the connectivity layer supports firmware updates using the protocol built on top here. So let's talk a bit more about the gateways. So the functions of a gateway in this case is either acting as a protocol translation between BLE and the IP-based network. It's also an integration point for other services, and you can sort of talk to multiple cloud services if you want to. It acts as a connection concentrator, so you can have a lot of devices that it speaks to the cloud on behalf of, and then you can do AI ML processing at the edge. On the sensor side, we need a bootloader. We need something that can give us the guarantee that you mentioned earlier about being able to roll back and forward. So one way to do that is to have a dual banking. So basically, you have one section of your storage on your microcontroller is for the actively running firmware, and then the other part is for the new firmware to be applied, and then the bootloader itself is just responsible for selecting which of these to run, and that's all there is. And then it's the application's responsibility to actually write the new firmware. And the reason for doing it this way is that then the application can continue to function as normal. Let's say you have a temperature sensor, it can still report the temperature data while it's being updated. And then the device is either connected using any protocol. If it's connected to the cloud directly using Wi-Fi, then the entire firmware update exchange is just like it would be between the gateway and the cloud. But if the device is connecting to a gateway, then you might need a custom protocol between over BLE, for instance, to do the update. So here's an example of an architecture where you have Drogue Cloud and integrated with a lot of different services. So on the top you have the sensors, which we just talked about, and then you have the gateways that could be scheduled by the OCM capability, but not all sensors go through the gateway. You also have external networks like the Things network, which sensors then talk to that network, which forwards the data to Drogue Cloud. And then on your Kubernetes cluster or OpenShift cluster, you have Drogue Cloud, which again integrates with all of these other systems, either Eclipse Ditto for digital twin or your custom integration, or you can also use the firmware update system, which is called Drogue Azure, which in turn integrates with Eclipse hawkBit. So this allows you to essentially use Eclipse hawkBit over LoRaWAN, for instance, if you want to. We also have another firmware manager called OCI, which stores firmware as container images, just as a reference, because a lot of the build tools for building applications on top of Kubernetes can use containers as a mechanism for storage. I'll show you that in a demo soon. So the first demo I'm going to show is where we have some device. In this case, it's a microbit. It talks Bluetooth Low Energy with a gateway, which in this case is represented with a Raspberry Pi 0. And then the gateway talks to Drogue Cloud, which runs on in the cloud on a Kubernetes cluster, along with hawkBit, which is used to manage the firmware. So this will show, A/B deployments. First having a working firmware, then you update to a new firmware, and then we'll also see how we can handle faulty firmware as well. So first, on the bottom right-hand side, we have the microbit, which is battery powered. You can see it having a battery a blinking A, which is the current version. On the bottom left, we have the Drogue console, which shows the events that are emitted from the microcontroller. You can see that it's just reading temperature. And we also have the firmware update console shown on the upper right corner. We have the microbit device. It has a hawkBit firmware type. It's fully synced, and it's running the expected version. So this state is continuously updated by the gateway. And then we have the hawkBit console, where we have a microbit target. We have 3 firmwares representing the different versions. So we're going to update to the version B now. And what will happen is that the Drogue firmware server will eventually detect that, it's supposed to be running this new firmware, and it will send the commands back to the device that now you need to update firmware for your device. So this commands goes via the gateway, which knows which firmware the device is running over the BLE link. So now you can see it started the update process, and once the device has written some blocks of data to its flash, the gateway will report back the progress to the cloud, which will then update this progress bar. And you can notice that it's still functioning as normal. It's still blinking, and it's also still reporting the temperature. At the same time, it's also handling this update process. And the state will be in this updating state until it's done. And then when it's done, you can see the microbit now has stopped blinking. Now it's in the bootloader state where it's swapping the firmware. And once it's done updating, it starts to blink B again. And it's also now reporting the temperature back in the Drogue console. So as it's reporting its status, it's will be marked as synced, both in the Drogue console and in the hawkBit. So that's showing the end-to-end using hawkBit. We'll also now try to apply the faulty firmware, which is designed to fail. This means that the device will not be able to run the new firmware, and it will roll back to the previous version, which is currently B. So we can see the update started. The target version is shown in the console, and the upgrade process is running. So in this case, I created a dedicated application in Drogue Cloud, and you can try this out for yourself if you run the sandbox. Use the Drogue Cloud sandbox and find this GitHub repository in my GitHub profile. And as the update is progressing, then the firmware is now being applied. You can see it stopped blinking, and then it's kind of taking longer than usual because it's not being able to run the new firmware, so it has to swap back to the earlier version. So once it's rolling back, it will start to print B again, report the temperature, and then when the cloud sees that, oh, it's still reporting the old version, it will try the update again. As you can see, it's resetting the update progress. So that's it for the first demo. So in the second demo, I'm going to show the continuous deployment concept. In this case, we're not going to be using Eclipse hawkBit because we don't have the let's say build pipeline to push artifacts to hawkBit ready yet. But using the container registry to store the firmware is a bit easier, because then you can use projects like the Tekton project, which is a way to build this CI pipelines on Kubernetes, and then package your application in a container, and then push it to the container registry. And in this case, our container is basically a firmware binary along with a metadata file, and then Drogue IoT will look at this container metadata to determine if an application or a device needs to be updated or not. The point of this is really to show that we can go the full cycle like any regular application, where you push changes to your GitHub repository, and then these changes are triggering the pipeline to build and deploy your firmware. So in this case, I'm going to use, since I don't have a lot of microbits, I'm going to use a simulated device. Basically, we have 10 simulated devices, which are and all of them are using the OCI firmware management. And we're going to trigger the pipeline, and then we can look in the OpenShift console that the Tekton pipeline is running. It's first fetching the repository. You can see the URL there, and you can try that out for yourself if you want. And then the build step will basically use, in this case, a Rust build container, which is able to build Rust firmware. But it can in principle be any, like if you're using Zephyr RTOS or FreeRTOS, something like that, you just need to provide a build container for that, which matches the which can run in Kubernetes. And you can see that this is really like building any other application. There is only one special thing about the build container, and that it's that it generates this metadata file with the version and using the Git revision and the size of the firmware that's going to apply. Then it pushes it to the internal container registry on the cluster, just like any other application. And then the simulated devices will eventually be reporting their status, and then get a command back from the from the firmware service that you should be updating. And now they're updating their state, and you can see they are progressing at different pace because they have a somewhat randomized interval between when they're querying the server. And eventually they will all be synced, and you have like a full end-to-end software delivery. And you can see the current version and the target version, they add up. Okay, that was the second demo. So to recap, we've seen how we can reduce risk by introducing this minimal piece on the device, being able to swap the two different firmwares. So this project is part of the Embassy open source project, which is a Rust, let's say, a runtime for doing tasks, handling tasks, asynchronous tasks, and also a hardware abstraction layer for a lot of embedded devices. We have enabled connectivity using some gateway, and there's a very many options here, but in our case we tried to demo the BLE way of doing things, because it involves a gateway, which is sort of one of the more problematic pieces of the puzzle. And then we used open source tooling. We used Eclipse projects. We used Drogue IoT to build this system. So you can try this out for yourself. The GitHub URL is for the firmware is in my GitHub account. You can use the public sandbox for testing out the device management. There's also a URL for the firmware management now. So just reach out to us if you want to try it out. There's more info on those pages. So that was what I had today. Thank you for listening, and I guess if we have questions, we can go for that now.
All right. Thank you so much, Ulf, for the great presentation and for the demos. There's no particular questions from our audience, but in all cases, I think if there is any further questions, everybody will be able to reach out to you specifically on various channels, email, Slack, etc. So I got one question from Ignore. He's saying, great presentation. That's a great compliment. Thank you. Could you kindly repeat what type of gateways you can manage with this framework?
So right now it's we're building out the capability using OPC UA as an example, but you could there's nothing gateway specific about this in terms of for Drogue IoT. So Drogue IoT will allow you to define some configuration in when you're creating your devices, and this configuration is just forwarded to the workload that is running. So that might be you have a container image for your gateway, which could be Eclipse Cora or something else, and then the configuration could be one of the be the parameters that you specify in the device configuration in Drogue Cloud, which is then forwarded to the gateway, and then OpenShift or Kubernetes this open cluster management will actually handle scheduling the workload on the edge, because it's part of this cluster management system. it's very early for us as we're just exploring the different ways we can integrate with this now. But we think it's a really promising way that allows you to manage the edge.
Yeah, so another question coming up from Victory as a follow-up: is it commercially available, or is it just a prototype at a prototype phase?
So Drogue Cloud is only an open source project at the moment. Although the open cluster management that we just talked about, that is part of OpenShift as ACM, or Advanced Cluster Management, I believe. But the IoT parts that I've been showing, that's still not a sellable or a sold product from that.
All right. I think with that, we're going to wrap up this great session from Ulf. Thank you again, Ulf, for this great session.